5-minute talks. And then, so we'll do all the talks and then like open discussion afterwards. Feel free to put things in the comments. If anybody, one person, sorry, I forget who was it who can't make it because they have COVID. Tristan. Tristan was going to give a talk. He can't because he has COVID, but hopefully he'll be fine. So right now, we're looking at Ravi and Tad signed up to give talks. But then due to the nature of this, if you want to give a 5-minute talk on anything, my audio is blurry. Is my audio blurry to everybody else?
I can hear you okay.
Okay. There's no loose connection because these are Bluetooth headphones. So we could try turning them off and turn them back on. But
it's the usual Zoom hassle.
Okay. Anyway, so we'll do the 5-minute talks. If anybody wants to decides on the spur of the moment they want to do one, just post something in chat. You can tell what I'm saying. All right. I will switch. I will put in a wire. 1 sec. What I'll do is I'll switch right when so let's have Ravi start talking, and then I will switch out right after that. Okay. So Ravi, why don't you take it away?
Sure. So I didn't prepare a huge talk because the prompt was about 5 minutes. So most I'm just going to talk a little bit about my background that's relevant and give a little bit about my current project and sort of where that might tie in. And it's more about sort of discussion from there. So I have mostly a software person, although one of the first startups I did was Hyperchem, which was doing parallel distributed molecular modeling for molecular mechanics, ab initio, and semi-empirical algorithms. So that was sort of where I got my start in nanotechnology. And then actually, as I gave a talk about that as my job presentation to Xanadu, which is where I actually met Eric Drexler. And he got quite interested in that. And actually, I think ended up having Autodesk acquire Hyperchem, which was sort of an interesting combination of events. Stayed in software for quite a while, then went back, worked on nanotechnology with Gail and Marty at Covalent Industrial Technologies for a year or two, which had been working on nanofiltration membranes. Then sort of back into software, working at Microsoft in a variety of roles around security and distributed systems. And about 10 years ago, moved over to Microsoft Research to work in genomics, and really got deeply into more genomics and computational biology, working on high-performance sequence alignment algorithms, cancer genomics, de novo assembly of the sugarcane genome, and also working on sort of commercializing some of this into pipelines, genomics pipelines in the cloud. The latest project I've been working on is called the Antigen map, and I'll give maybe just 2-minute overview of what that is, which is basically using machine learning to, am I able to present here, by the way? Yeah, okay. Which is apps. How do I sort of never presented in share screen? Here we go. So what's going on is basically, if you think about the way your immune system works, it's generating a bunch of these T cells and B cells, and particularly we work with T cells, that have a unique genome that's created through recombination as they're formed. These float around in your bloodstream. They get filtered out to avoid autoimmune disorders. Most of those get filtered out in your thymus as self-reactive. And then what happens when you see a pathogen is your body breaks it up into little protein fragments and presents them on the surface of the cell, bound to a molecule called HLA, of which you have several dozen different flavors. And then TCRs that happen to bind to that antigen in HLA will get activated, will go back to the thymus and will replicate. And that's one of the ways in which your immune system has memory. And so that's how when you see that same antigen again, instead of having to rely on a 1 in a billion chance of running into a COVID TCR, you'll have millions of them already floating around in your bloodstream. You will react more quickly, and your immune system will get in gear to actually to work on that and to kill infected cells. And so, you know, the sort of thing that we do with that is mostly machine learning on sequences. But the other interesting area here is if you think about what's actually going on in the TCR antigen HLA binding is like a three-way protein folding and docking problem. And so we've actually started to experiment. We have some in vitro methods of trying to find out which TCRs bind which antigens, but we're also exploring some of the molecular modeling approaches where we might be able to actually do this in silico and we can run scalable experiments because we can find these TCRs and we have some ways of knowing which sort of portions of the let's say the SARS-CoV-2 genome they target, but it's not, it's pretty expensive to do that experimentally. And our goal with this is sort of, can we do this computationally? And it's certainly, there are some limits, but we're starting to make a little bit of progress on that. So that's probably enough for 5 minutes and give people a chance to think about that and whatever topic. So my area of sort of current work is more around proteins rather than sort of carbon diamond or other kinds of nanotechnology, but certainly very interested in biology and biological applications.
Awesome. Wow, you are. That was literally, the alarm went off right when you stopped. That was very impressive. How's my sound now, by the way? Good? Okay, cool. I am on
That's
a
better.
wired connection. Okay, like, unfortunately, that's the state of the world. Cool. I have questions about that. But first, Ted's going to go. And anybody who wants to do something on the spur of the moment, the opportunity is still there. So take it away, Ted.
Can I share my screen?
You should be able to. I changed the security settings, so everybody should be able to
Okay.
share their screens.
Can you see the screen? Like in machines? Is it working? Hi, so I'm Tad Hogg. A long time ago, I used to work at Xerox PARC and Hewlett Packard Labs. Now I'm affiliated with the Institute for Molecular Manufacturing, a Foresight sister organization. And I thought I'd just go over a few sort of general ideas, mostly to kind of promote brainstorming of how I can see computing and control fitting in with our discussions of molecular machines. So I see three big areas in computing to help discovery of molecular machines, the control of the individual machines, and then for applications, designing the behavior of large numbers. And I'll talk briefly about each of these. For discovery, sort of the obvious thing is to use simulations to look at proposed machines that we cannot yet build. And then there's, I think, a lot of opportunity for machine learning to help us design machines and also how to fabricate them. We heard a little bit about this in the meeting, I guess it was 2 weeks ago. And there's a variety of different possibilities there. When we talk about individual molecular machines, our big problem is, I think, is that we have very poor engineering intuition for how these machines work. They're so different from what we are used to with our conventional engineering. Two particular issues, thermal motion. So unlike your car where you turn off and it just sits in the parking lot until you come back for it, a molecular machine is constantly moving around even when you quote unquote turn it off. So it'd be like if you come back to your car and it somehow diffused around in the parking lot somewhere from where you left it. We had a nice discussion of that, I guess a year ago in this Foresight series. The second one is that viscous damping is far more important than inertia. And since we haven't talked about that yet, we decided to give an example. So imagine you have a molecular machine that, say, is using a piston to try to extract energy from acoustic or ultrasound. And you can contrast this with sort of our normal Newtonian physics view of the world versus when viscous flow is dominating. So let's see if this animation works, and we can talk through it. Can you see the animation? So on the left, you just imagine this is a really, really heavy piston. And so when you're not pushing it, it's just coasting, so that when the pressure is zero, when it's white, as right now it's coasting. Now you have to push against it to slow it down, then you speed it up, then you push against it to slow it down, then you speed it up. That's dominated by inertia. That's not the way molecular machines work. They're much more focused on dominated by viscous behavior, which is kind of like Aristotle's view of physics. So if you're not pushing it, it doesn't go. So here you see when the pressure is zero, that is, and it's white, this piston is not moving, and it's always moving in the direction that you're pushing it. Another big difference between these is that the inertial case, you can store and recover energy, say in a compressed spring. Viscous is always dissipated to heat, so you always have to worry about dissipation. So that's looking at a property of individual machines that we have to keep track of as we think of designing them and have some computational tools that may help us. When we think about applications, in order to get some macroscopic effect from molecular machines, you need a huge number of them. And there's also going to be significant noise in the environment, and then machines might not work that well. And they're also very likely to have very limited onboard computation. So the kind of controls will have to be very simple. You put those properties together, and then you immediately think, these are like swarms. Simple devices, lots of them, simple behaviors, and the swarm as a whole can do some useful things. I'm going to give you an example, two examples actually of this. First, one from my work is thinking about acoustic power for microscopic robots. So this is a generic schematic of a robot with lots of these pistons that I showed you earlier. And just to give some context of size, on the right is the robot shown in the context of some blood vessels. So now where does the swarm come in? Well, if you have a large number of these robots all extracting acoustic power, they're going to be attenuating sound like crazy. And so it's going to mean that there's not as much sound deep in the body as there is near the surface, but the robots could use swarm behaviors to alter where that sound goes. And that's an example that a good swarm behavior can help the robots distribute power where it's useful for them. The second aspect is programming swarms of molecular machines, separating the control of individual devices and swarm task control. Agman's group has done an interesting example of this for DNA nanorobots, including reconstructing a scenario from one of Isaac Asimov's short stories on 3 laws of robotics, which is a fun application. So let me summarize. I think molecular machines they're difficult to make, understand, and control. Computer-aided design has lots of opportunity to help with this. Hardware and software can each help each other. And we will need multiple CAD tools that play nice together, covering a wide range of space and time scales. So no matter where it is that you like to work, whether quantum all the way up to these swarm behaviors, plenty of opportunities for helping us understand molecular machines. There we go. Thanks for your attention.
Also, thank you, Ted.